help it skip across the water. And the reason it can do that at all is the same reason you can flip this jar upside down and not get wet. How can you outsmart water? This smooth-talking physics whiz is going to show you that it's all about tension. Surface tension, that is.
So I've got a jar here about half filled with water. What do you think will happen if I flip it over?
No, it's gonna make a big mess. No. What are you doing?
And if I put a lid on it and I'm really careful, so far it's all right.
Yeah, but you're holding it.
Now,
As the water touches the coaster, it spreads out evenly, which is essential to what happens next.
what do you think will happen if I take the coaster away?
The water's gonna spill out.
Let's see if that's true.
What?
The water does just fine by itself. But how? The surface of any liquid acts like it's got a thin membrane stretched over it, because the molecules like to stick to each other even more than they like sticking to other things. Molecules on the surface have no neighboring molecules above, so they exhibit stronger attractive forces upon their nearest neighbors. The smaller the surface area, the greater the surface tension. So by dividing the surface area of the jar's opening with this screen, you greatly increase the surface tension, enough to support the weight of the water. It's a precarious balance though. You can puncture 1 or 2 membranes and it's still okay. But change the weight distribution too much and...
Gonna eat that still?
A functioning eye relays an image to the brain in just 13 milliseconds. But it turns out that we perceive the objects around us with more than just our eyes. So then, is it possible for a blind person to see?
Sight is a complicated thing. Taking in visual information with your eyes is just the first step. We need our brains to make sense of that information, and we use 2 distinct areas to do so. There's the ventral pathway that identifies and recognizes objects. It tells you what you're looking at, like your friend Bob. Hi, Bob. Then there's the more primitive dorsal pathway. It senses where things are in relation to yourself, like that speeding car. You need both pathways to see properly. If one is damaged, you get this. This man is blind. Lesions on his ventral, or what pathway, prevent his brain from processing and therefore seeing his surroundings. Yet he can sense the obstacles in his path because his healthy dorsal pathway still subconsciously tells his body where things are. This dual system of sight processing can also trick your brain. See those purple circles? They're actually the same exact size, but when they're surrounded by smaller circles, they look bigger. The effect is even more pronounced when you put it in motion. That center circle is staying the same size. It's called the Ebbinghaus illusion. This illusion is named after a German psychologist who first discovered it. Your brain thinks the purple circle is growing and shrinking because your where pathway can sense that the center dot is not moving closer or farther away from you. But your what pathway recognizes that it's the same circle, so the only solution your brain can come up with is that the center circle must be changing size. So, is it possible for a blind person to see? Yes. The same dual visual system that's tricked by the Ebbinghaus illusion allows people who are blind to still sense their surroundings. Research has proven what moms everywhere already told you. Ripping off an adhesive bandage is less painful if you do it quickly rather than slowly. So why the need for speed? Turns out that the same thing that makes your owie a little better also makes for a great bar trick. Why is faster better? This suave scientist is about to show these folks with a bet none of them can refuse.
I have a challenge for the 2 of you. You can have this $5 bill, but there's a catch. You can't touch the bottles, and you can't knock them over.
Let's see.
I'm usually good at these things.
You think slowly will work? Like if I just weasel it out?
She's got the gentle touch. Oh, oh.
That wasn't very successful.
So here's a hint. Treat it like you're ripping off a bandage.
Oh my God!
Hey, all right. Oh, that was close. It was close, right? Yeah. The reason this works is because of Newton's first law. An object at rest will tend to stay at rest unless acted upon by an external force.
The bottles don't want to move because of a property called inertia. So the quicker you pull, the less you're fighting that inertia. Just like yanking off a Band-Aid. So why is faster better? Less pain and no broken beer bottles.
So, are we both gonna get a 5 or?
He gets the 5, I think.
All right, I will see you guys later.
Did you know that in its undisturbed state, ice is not slippery? I know, try telling that to these people. But frozen water isn't slippery all on its own. Why do you slip on ice?
Would you like to help me with an experiment today?
Sure. Yeah.
Sure.
All right, so what we're gonna do is we're gonna take these 2 counterweights with this wire and we're going to lay them across this piece of ice. What do you think will happen to the ice?
I think the ice is gonna break.
Seems reasonable. You wanna try it?
Yeah, I'll give it a shot.
All right, cool. Okay, get it centered there, and we're not actually gonna let it go, but right there's good. So what do you think's actually happening right now?
I think the wire is gonna probably split them into 2 separate cubes.
So you think the wire's moving through and the ice is actually kind of falling apart?
Exactly, yeah.
Well, the wire is sinking into the ice, and ice isn't cracking.
Yeah, yeah.
Which is shocking.
It's in the middle there, but it kind of seems solid on top. So I guess as it's splitting, the ice is just forming back together again.
Yeah, it's a really interesting phenomenon that scientists actually don't fully understand. It's called regelation.
Regelation is what's at work when you ice skate. The friction of the skate causes the ice to melt a little, enhancing its slipperiness, but then it refreezes, as if nothing ever happened.
Check it out.
No. Are you serious?
It's all one piece.
That's crazy.
It's still got the line for the wire. That's so cool.
Oh my goodness! Look at this!
Isn't that crazy?
Oh, this is fabulous.
It's all one piece.
So, why do you slip on ice? You don't. You're actually slipping on a microscopic layer of water created by the pressure you put on the ice. And it will refreeze as soon as you slip away.